everybody. Thank you all for coming. My name is Nicholas Matsakis. I'm going to talk about Rust. And I imagine a lot of you have heard about Rust, but I always like to start, just in case, with a quick summary, kind of what is Rust all about, from my point of view. And I think one way to look at it, the high-level view maybe, or maybe what we thought when we started out, was you have this kind of gap in languages that are in mainstream widespread use today. Or you can use C++, and you will get a lot of control over your machine, and you get lots of flexibility, and you can build complex systems, but you have to put up with kind of all of these horrible bugs, right, that are the nightmare of systems programmers everywhere. And most modern languages, I would say, have chosen to resolve this by, well, you give up a little control, and you give up some flexibility, but you adopt a garbage collector. And in exchange, you get freedom from all these bugs. Well, almost all. Right? It turns out a garbage collector doesn't really help with data races. So if you write, like in Java, for example, you'll have all the same problems that you would have in C++. And so there's kind of a gap there, an open problem. And you also have this loss of control and flexibility, right? So you've kind of given over some part of your runtime characteristics to the author and engineer of the garbage collector. It might or might not fit your needs. So what Rust tries to do is to take a different approach, right? We give you the control, we give you the flexibility, but we stop the bugs. Oh, and as a bonus, we're going to stop the data races too, while we're at it. And then we're going to do it with static checks. So that's like the nutshell pitch of Rust. But if I had to put it into one word, what I think Rust really does for you is it's an empowerment tool. It kind of gives you the ability to do things that you couldn't do before. Not necessarily couldn't never have done, but couldn't do in the time and resources and so forth, and with the team you have that were allotted to you. Now, I can tell you, maybe not in this room, but in other rooms, telling people that using a static type system is going to make them more powerful is not like the easiest pitch, the easiest sell. They sort of see it as like a spinach, their parents are coming and making them eat it, and they really want to ship some product and get it done, right? But I feel like they're right. It is spinach, but it's like Popeye spinach, right? It's like the spinach that after you eat it, you get stronger, and you can get some, you can do things that you never quite were able to do before. And I'm going to spend, I have a bunch of stories like this, right? But I'm going to spend some time talking about some experiences at Mozilla along in this lines. And if you're interested, we have these white papers online that talk about other companies, because one of the things that we didn't really expect, but we found in the course of working on Rust, is that we originally were targeting sort of wizened systems programmers, well, I shouldn't say wizened, experienced systems programmers, like the ones at Mozilla, right? People, C++ hackers and so on. But actually there's a much bigger audience that has been avoiding systems programming because it's too difficult and it wouldn't make sense for them, that are attracted to Rust, right? So Tilda is an example of a company that was working in Ruby, wanted to improve their performance and memory usage requirements, but didn't want to take on C. They couldn't get that to work reliably enough. And Chucklefish is a games company. So as far as Mozilla goes, earlier this year, there was a new Firefox release, you may have noticed, called Quantum. I should mention I work for Mozilla at this point, so you should be using Firefox. But one of the things that Quantum did was make Firefox a lot faster, right? And there was a lot of reasons for that, but some of them were because we adopted a new style system, CSS layout and so forth, implemented in Rust. And one of the cool things about this style system was that it was parallel. Now, style layout, is basically this embarrassingly parallel process where for any node in your HTML tree to compute the styles, which is basically like how should it appear on the screen, you only have to consider the parents in the tree, right? So all the siblings can be processed in parallel. And everybody knew this. And everybody wanted to do it in parallel. Like there was a Bugzilla bug, for example, first reported, it's a little hard to read, first reported 7 years ago, saying, hey, let's parallelize selector matching. And if you go read the history of this bug, it makes for a good case study in sort of where it can be hard, why it can be hard to do things in C++ sometimes, right? Even embarrassingly parallel problems. And there's a variety of problems, everything from the Microsoft compiler didn't work quite the same way GCC did in some particulars, to data races that were hard to find. But I think the bottom line was they could have built a system that they felt they could maintain over the course of years with people coming and going and working reliably in all that time. right? Even if you could get it to work for the first release, can you keep it working release after release? And it just didn't seem like it was a good fit. But doing it in Rust did work, and it's a good story. There's some good talks from Rust Belt Rust, for example, talking about all the things they had to deal with that you can find online. But it's shipping now, and it's interesting in another way. So this is from a blog post that I'll give a link to in a second, showing different parts of the quantum changes that we made. And what's interesting is 2 of those components are written in Rust, but the rest are written in C++. Right? This did not require a full rewrite of all of Mozilla's layout engine and so forth. We were able to insert it and interoperate, which is definitely useful if you're trying to adopt something. And the quantum renderer is not yet shipping, but will be. That uses the GPU and Rust and the GPU in conjunction to do rendering. So if you'd like to learn more about that, check out this Mozilla Hacks article, and check out everything by Lynn Clark, because she is awesome, and all her articles are great. But I think I've given you the hard sell of Rust now, so I'm going to go into sort of what the meat of the talk, right? And what I want to do is something a little different than I've done in other Rust talks. I'm going to start by talking about the design of Rust. So how we use ownership and borrowing, and how we achieve safe parallelism, and the role of unsafe code and some other things. And then I'm going to spend some time talking about how we design the process of designing Rust. Basically, what it's like to run an open source project, some of the things we've done right and some of the things we've done wrong, more of those, and basically lessons that you might apply if you're trying to do something similar. And I think these apply not only for open source, but possibly for distributed computing groups and other things that can have a similar character. Any group that gets big enough starts to run into these sort of consensus and design issues. So let's start with the design of Rust itself. I mentioned parallelism a few times. This is a picture of David Barron. He's a distinguished engineer at Mozilla, very good programmer. And he has this sign up above his desk that says, "You must be this tall to write multi-threaded code," right? And it's like way up there. So that's kind of expresses the prevailing sentiment, at least at Mozilla, and I think at a lot of places, about writing multi-threaded C++ code. It's just too hard to do it reliably, except in very particular scenarios. And a big part of the problem is this problem of data races, right? And if you want to define what a data race is, it's kind of the conjunction of these 3 situations. You have 2 threads accessing the same memory, that's the sharing part, and at least one of them is making changes to it, that's the mutation, and they're not coordinating. There's no locks, there's no ordering between them, and in that case you get a data race, which is a kind of undefined behavior of your program. It can do anything it wants, at least in C++. And usually we address data races by knocking out one of the elements here on this page, right? So if you want to go with sequential programming, then everything is ordered, so you can't have a data race. Although I would argue you can have a lot of bugs that look and feel a lot like data races, like some of the causes of segmentation fault and so on. But strictly speaking, you cannot have a data race. Or you could knock out mutation, and then you have a functional language, like Haskell, and then, okay, you can't have a data race again because everybody is reading the data. And finally, you could take sort of the actor approach and knock out sharing altogether and just have these isolated vats of memory that exchange messages and so on. But each of those kind of comes with a pretty severe trade-off in terms of the control and flexibility that we're trying to keep when we're doing in Rust design, right? So what we adopted is something a little more nuanced. We don't take out one of these legs altogether, but we take out the intersection of sharing and mutation. So you can't have 2 aliasing pointers that are both mutating the same memory at the same time, right? You can share, well, we'll get to it. You can share or you can mutate, but not both. And so how do we do that? Well, we build on a lot of great academic work, is how we do it. We call this system ownership and borrowing, but there's a lot of names for this in the literature, like linear types and ownership types are the 2 most common, I would say, or affine types, strictly speaking. But the idea is, at least the way it works in Rust, that you're interacting with memory in these kind of 3 main ways, right? When you have a value, let's say, of type T, that's sort of the default way, that means you own that value. And when you own a value, you're the only one with access to it. And nobody else can touch it, So that means there's no aliasing whatsoever. And we're going to see that that implies that we will permit mutation. So let me give you an example. This is some Rust code. And we have a function here. Can everyone read this out of curiosity? Okay. We have a function here and another function over there. And we're going to walk through it and see what they do, what it does. And the first line, by the way, these pictures were drawn by my daughter who wanted to contribute to the talk. They're so much better than what I had before. So the first line says let apple equals apple new. And what that's going to do is apple new is not a keyword in Rust, it's just a method, in this case attached to the type. It's going to construct a new instance of apple and return it. And when you get that new instance returned to you, you will have ownership of that value. Right? So this is going to create an apple and give ownership to the local variable apple, which is in turn owned by the function, right? Represented here by this young lady. So we have the apple, and then we're going to call, which is owned, and then we're going to call the eat function. And the interesting thing is here. So eat takes one parameter of type apple, but what that means is that eat is going to take ownership of this parameter. When it's given the parameter, it's the only one that has access to that particular apple in the system anymore. Right? And that's very different than, say, Java or something like that, where you both now share access. And on the other side, when we call eat and we just give it apple as a parameter, that means we're giving up ownership so that eat can have it. So eat will take ownership. So when we actually invoke eat at runtime, it'll come along, and logically speaking, the ownership of the apple transfers over. The actual runtime semantics of this are the same as what would happen in C. Basically, we'll copy the fields of apple over to eat. But the runtimes, the logical semantics differ. And so now the apple has a new owner, which is the eat function. It can execute. And when it finishes, whenever we exit any scope, basically we take all the things that were owned by variables in that scope that have not been given away, and we free them by running the destructor in C++ terms. So when eat returns, the apple is going to get freed, and the memory is reclaimed, and that's deterministic, right? There's no garbage collector involved. And then we come back, and now you might be wondering, well, what happens? We've given away our apple. What would happen if the code were to try to go on using it? And the answer is that you'll get a compilation error, because the compiler tracks what you create, what you own, and what you've given away, and it doesn't let you give away the same thing twice. So let's look at a slightly more complicated example. Same idea, but now I'm going to have some more data structures. So I made an apple the same as before. But on the next line, I'm creating a bag, which is just a vector. When I call vec new, I get a new empty vector, and I own it. And now, when I call bag.push, or one second, before I get there, you see I declared this bag as mutable. I said let mute bag. In Rust, local variables and all the things that they transitively own are immutable by default, unless you say that they should be mutable, which kind of helps you to know when you're reading your code what's happening. In this case, we're declaring the bag mutable because we're going to be putting things into it. We're going to grow the vector that's mutating it. So we have a mutable vector. And when we call bag.push, again, we're passing it the apple, so we're giving up ownership of our apple. And in this case, we're transferring it not to another function, but into the vector. Right? So now we have, we own the vector, and the vector owns the apples that are in it. In this case, there's just one. So then we could call bag.push again. We'll have two apples. And finally, we can call this deliver method. And here you see deliver takes a vec of apples. That's our generic syntax. And it's, again, going to take ownership of this entire vector. Right? So, and we're going to give up ownership. So when we call, basically the same thing happens, except now deliver took ownership of the vector and transitively all the apples within the vector. And so when it returns, it will free that vector, and that's how it works. And so this is basically memory management in Rust. And one thing you'll notice is there's no mallocs and no frees and so forth. It feels very high level, but it's actually happening kind of deterministically based on these rules of who owns what and when you exit a scope. Okay, so that's how ownership transfer works. But if that's the only tool you had, it would be kind of annoying to write programs, because most functions don't actually need to take ownership of the data that they're working on. Usually you're just reading some stuff and computing a new value as a result. And so we have this notion of borrowing. And the most common kind of borrow is we write %t, and that's called a shared reference. Right? And the reason it's shared is we'll see that when you have a shared reference, you can make many copies of it, and they all can access the same data. But in turn, that means that you have to have no mutation. So if we go back to our example, if I have the same bag, and now instead of calling deliver, which needed ownership of the bag, I'm calling weigh, which is just going to measure the weight of the bag. Right? And that can take not a vec of apple, you see it has an ampersand in front, it's taking a shared reference to a vector of apples, so it's borrowing this vector, essentially, from the caller. And on the other side, we don't pass bag, but rather we pass ampersand bag, which is an expression that will make a reference to the bag and pass it in. So now, when weigh gets called, it's going to just be given a pointer at runtime into the caller's stack frame. And you can see also, just as an aside, that arrow U32, that's the return type of weigh. So it's going to return a 32-bit integer. And one of the things that's nice is because it has a shared reference to the bag, you can use this to make more shared references, as many as it wants. And these are sort of potentially overlapping, because now we have one reference to the bag and more references to the apples in the bag. And those are this sort of, you can reach one from the other, so they're overlapping. That's okay. It's an aliasable shared reference. Everything's fine. And when weigh returns, all those references just sort of go away. And no memory gets freed, because it wasn't the owner of that memory. So let me drill into this just a little more to give you a better feeling for what it means for something to not be mutable. Because in Rust, mutation isn't really a binary notion. It's not mutable or not. It's rather, is it mutable at this point in the program or not? Right? So when we start the first line, we're making this bag, and we declared it to be mutable. So it's mutable sort of when it's not shared, is what that means. And in particular, initially, we can go ahead and, as we saw, we can push into the bag, and that's just fine. But when we make a reference, so this says let r equals ampersand bag, then we're going to start sharing. And the way this works is that we will statically compute, so at compilation time, figure out how far, what regions of your program are using that reference. Until the last use of the reference, that span of the code is where we consider bag to be shared. And so in this region, you won't be able to mutate the bag. So that means I can go ahead and use the variable bag to read things, like compute its length, and that's just fine. But if I were to try to call bag.push, I'm going to get an error. And this comes back to that rule about sharing and mutation, because now, exactly here, we have two ways to name the bag. We can go through the variable r, and we can go through the variable bag. In fact, we can make many more ways by copying r. So that's why we can't allow mutation. Right? But similarly, of course, we also can't mutate through the name bag, nor through any of the references that we made, because they're only shared references. They don't have that capability. But once we're done using r, then we can go ahead and push onto the bag again. So this is only a temporary thing. Okay, so let's look at the last thing then, which are these mutable references. So here, I have let r equals ampersand mute bag. So it looks very similar to the previous example, except now we've made not an ampersand bag, but a mutable reference. And what that means is we're going to again compute the region of the code where this reference is in active use. But in that region, instead of allowing only reads to the variable bag, we're just not going to allow any accesses at all. So the only way to get at the bag is through the new reference that we made. So we can call bag, or if we call bag.len, we'll get a compilation error. But if we try to use the new variable r, that's just fine. That's our reference. We can push onto the bag or read. We can do either thing. But once the reference is out of scope, we recover access to the variable bag again. Okay. So that's the basic ownership and borrowing mechanism. Right? And what I want to show you now is how we build on that. Yeah, did you have a question?
So you mentioned that when the reference r goes out of scope, could you nullify, if you nullify r explicitly, can you is it possible to like nullify R to like reclaim ownership somewhere else or release the?
I mean, if you simply stop using R along some path, you don't have to actually nullify it. Then in the portion that is sort of dominated by the lab, that like where you stop using it, then you will just be able to use back again.
So there's like some fractional permissions happening behind the scenes?
It's not implemented as a fractional permission, but that is one way to model it. You know. You could talk to Aaron about that. Right, so I wanted to show how we use this ownership and borrowing, and in particular around parallelism. And there's an observation that I would make, which is that there's been a lot of really great work on building really nice to use parallel abstractions. And it's not really easy, but it's relatively easy. But what is really, really hard, especially in mainstream languages, is like helping people to use them correctly, right? So, for example, Go offers these really great channels, and this is a bit of Go code, and you see here what I'm making a hash map, and I'm sending it over a channel, and that's a very nice, well-implemented, efficient library. But there's nothing in the language that stops you from going ahead and using the map that you just sent over the channel in the thread, or the Go routine, I guess, that sent it. Right? So you can wind up very easily with data races. Go has a dynamic data race detector and so on. This is not a slight on Go, I should say. Like I said, it's just a generally hard problem, especially when you have aliasing all over the place. But it plays out rather differently in Rust because we have the ownership and borrowing tools. Right? So, for example, this is the equivalent to that Go code. And in Rust, and I'm making a hash map, and I'm calling this channel.send, and I'm giving the map as argument. And if we go over and look at how the channel is implemented, that's the signature of channel send. Let me walk through it a little bit. So this impl, that's Rust syntax stands for implement. It's for adding methods to a type. So I'm implementing channel of T, and T is the generic, the type of data that goes through the channel. And you see that the send method takes ownership of its argument. Right? It's just taking ownership of this value of type T. So what that means is the caller has given ownership away. So if the caller were to go on and try to use the map that it sent over the channel again, it's going to run into errors, just like we saw with the apples. So just by the sort of building on ownership and borrowing, right, we can enforce this transfer of ownership across channels and so forth. And there are similar things that apply to other parallel paradigms. So this is message passing, but and also I should add, again, we did not invent the idea of using ownership here. This is like one of the main reasons ownership types and so on came around. It's a really nice technique. We're building on it. So the fork join, another nice pattern would be kind of doing fork join programming where you want to launch off a bunch of threads to process some data and then wait for them to finish before you go on. So this might happen if you have like a for loop that you'd like to do in parallel, for example. So let me give you an example how that plays out in Rust. So this is a sequential code. It's using Rust iterators to load a bunch of images from the disk. Right? And the way it works, first you have this function load images. It takes as reference a shared reference to an array. That bracket syntax means an array. It's an array of paths. So it's going to be paths into the file system. So it might be like a.jpg and whatever, b.ping. And then it's going to call paths.iter. What that does is it gives you back an iterator yielding up references to these paths. Now, iterators in Rust are lazy, so this doesn't actually do anything yet. It just makes an iterator. And then we can build on it. So we can call, for example, .map, which will say, kind of for each of those paths, I want to load an image. And now I have an iterator over images, but none of this code is executed yet because it's lazy. And finally, I call .collect. And that's the point where we're actually going to drive the iterator, start pulling the paths, loading the images, and building them into a vector that we're going to return. So that will execute one by one. And these are also my daughter. One of the nice things at the hospital in Zurich where she was born is that they take the picture on the same day. It's really cool. You should all go there. For having children. So, okay, that was a nice loop. That was sequential execution. But what if I wanted to run it in parallel, right? So there's this external crate called Rayon, which I wrote initially, and now I maintain it with some other people. And it's useful because it lets you convert these sequential iterators into parallel iterators. But I want to highlight something about it, which is that it is an external crate, which is Rust term for library. In other words, this is not built into the language. The language actually knows very little about threads, apart from a notion. We have some like primitive intrinsics for doing atomic reads and writes. Other than that, it's all built in the library, which is very much by design. Right? Rust is meant to be a language where libraries add all the major functionality. So it's a third-party library. And the main thing I've changed here is instead of saying .iter, I wrote .pariter. And now when I execute this, all these pictures will load in parallel. It uses a work-stealing library based on SOAP-like techniques and so on. And what I would observe here is that this is really nice. It is something that you can do in a lot of languages. Scala has similar things. I know for sure. I'm not sure what other languages, but I'm sure many. But there's something else you can do in those languages too, which you can't do in Rust, which is sort of trivially create data races when you're using these tools. So an example might be, suppose that I were to modify that iterator, not just to load the images, but I wanted to count how many JPEGs I saw as I went through. So I might add a variable equal to 0. I might check this path ending in .jpeg. Then I'll increment my counter. And of course, that's fine in a sequential loop. But if I try to run that in parallel, I'm going to have this problem of two threads mutating back, and I don't know. Who knows what you're going to get in the end? Right? You're going to get probably some number. It probably won't be the right number. You might not notice that it's the wrong number for a long time until it causes you a problem down the line. So what happens in Rust, though, is that this code just won't compile. And I don't have time to go into exactly all the mechanisms why. It comes out through a variety of desugarings, basically. But it boils down to a violation of that same rule that I was talking about before. So what happens is you have this closure that I've pulled out here, and the way that that closure modifies the local variable JPEGs is by having a mutable reference to it. So it's mutating through this reference. And that implies that you can only use that closure if you have you can only call that closure if you have a unique access to that closure. So you can't call that closure from two different threads because they would be sharing access to the closure, and it needs unique access so that it can do the mutation. So this gets you an error, and that's very nice. And when I give this example, actually I usually give a slightly different one, but it's similarly kind of obvious what the data race is. And I always thought this was so simple. Like nobody would ever make a mistake where it's just in the same function, such an obvious data race. But actually, this catches bugs for me all the time when I'm using it. I probably would have found them pretty quickly when I ran the code, but it's still very nice to just say, oh, right, I copied and pasted wrong, let me tweak that, just in the compile cycle, right? And I think that's a factor of this empowerment I was talking about, just helping you not even have these obstacles while you work on a bigger design. So that's how fork join processing works. We have also support for other things. There's, of course, locks and a way to model locks. There's a great library of lock-free data structures, and Aaron Turan has done some stuff now carried on by others to do sort of epoch-based reclamation and so on. And we're working very hard on futures at the moment. So that brings me to the last part where I sort of lift up the covers a little bit. So far I've been showing you all this beautiful statically checked code, but there's another layer underneath, which we call the unsafe layer. And that's kind of key to how Rust works, because the idea I mentioned that we want to build everything up in Rust as libraries, right? So the idea is that we have this core language that has a relatively simple notion of ownership and borrowing that I can explain to you in a few slides. But then we have all these libraries doing other stuff, like work stealing and accessing the file system, and even stuff relatively simple like maintaining reference counted pointers and so on, which don't quite fit that paradigm, at least not the way they're implemented. And the way that they work is that they make use of unsafe blocks, which is basically a bit of code where you're telling the compiler, trust me, I got this. You don't have to enforce all your rules. And in exchange, you get the right to use C-like pointers, which don't have the same constraints that Rust pointers do. But the idea is not that you kind of just sprinkle this through your code whenever it causes you a problem. You could do that, and you're kind of back where you started, but rather that you build up abstractions, right, like the ones I've been talking about, that offer a safe interface to the world, but are implemented in some complex way. And I think every language has this. Sometimes they call it an FFI, but they have it somewhere, some way to kind of bridge out. And the nice thing about this is that, for example, the whole Rust ecosystem doesn't involve any C. Right? It's all Rust from the ground up because we have the ability to use unsafe code to do the lowest level stuff that we have to do. So that kind of brings me to the end of this sort of high-level view of the design of Rust. There's a bunch of stuff I don't have time to cover. We have, for example, a type class-like system we call traits, if you're familiar with that from Haskell. We have a really great package manager, which is also essential and part of this empowerment strategy, because anytime you sit down to write a new C program, like, first thing you do is go find your hash map and copy and paste it from your old project and all that stuff, right? You don't have to do that anymore, nor your makefile. I had a friend who thought that there was no makefiles, that there was only one makefile, basically, and everyone just copied and pasted from that one to make new ones. I think that was probably true. But what I want to talk about now is more how Rust community works, right? And I had this idea both because it's something we've been thinking about a lot lately, but because Jan Vitek asked me to talk about the hardest thing that we've done in Rust. And the technical challenges in Rust, like, are hard. So I thought about those at first. And but they're not the hardest part. In some way, the hardest part has been figuring out how to work, how to make the Rust into a functioning community, and how to have it, in particular, be the kind of inviting and welcoming community that we want it to be while still doing all the work that we want to do. So there's this quote here that says, as always, the hardest problem in computer science is people. And that kind of has this, I don't know, I hate all people sound to it, but I think it's not quite as simple as that, but there is definitely truth that people are complicated, and figuring out how to structure the system with the right incentives is complex, right? And so why do we think this is so important? I mean, I think there are a lot of reasons, but one of the reasons is Rust is all about finding and sort of eliminating trade-offs in some sense, right? We want to have all these traditional dichotomies and get rid of them. And say, you can have memory safety without garbage collection, and you can have threads without data races, and so on. And really what that's about is not really eliminating the trade-off. It's more finding a hidden variable somewhere, a different approach, such that you can kind of extract the nut of the conflict and leave the other parts behind, right? And to do that, so when it comes to sharing a mutation, I think the thing would be that there's this time factor. Right? It's not just about are you sharing or mutating, it's about when you're doing it. And in order to do that, you really need to have a lot of people sort of giving insights into the problem, because it's exactly the thing that you're not thinking of that is probably the thing you're missing. It's making this conflict seem intransient. And so the way I like to imagine it, if you all remember Captain Planet, is that we're like all coming together, all these different communities. There's like academia and C++ gurus and JavaScript hackers and Rust folks and new developers, and together we're building this beautiful language. That's often true. Sometimes it's a little bit different. Sometimes it's kind of like this, where everybody's sort of pulling for what they want, and in the end nobody gets anything nice. And so trying to find a path that leads more towards the former is exactly the thing we're after, right? And a big part of this, and where I wanted to start, is kind of what are the techniques for growing up big teams of people on an open source project? This is something we've been thinking a lot about lately, because you can always use more people. And if we want to do all the things we want to do, we need to scale up. If you look at this is a chart of Rust's, the number of people involved in Rust governance over time. The first thing that's kind of interesting is that it starts around 2015. I started working on Rust in 2011. And in between there and here, we didn't really have a formal governance system at all. So this is kind of step one. If you want to grow your open source project and so on, you probably do want to start establishing a more formal system. It doesn't have to be very complicated, but just recognizing and naming the people who are really heavily involved is a really good thing and very important for them to get recognition for all the work they've been doing, right? But you can see we sort of stayed static for a while, and then we sort of noticed that. And we started to work consciously on how to improve. And it's made a big difference in terms of the number of people that we've been able to incorporate. And I think that this is kind of a key part of our philosophy, is that open source doesn't just happen. Right? There's a notion that I certainly held, and I think a lot of people hold, that open source is like you put the code up, and somebody comes and they say, that's cool, and they open a PR, and then together you're working, and it's just sort of this serendipitous accident that everyone is collaborating and driving it forward. But actually, Well, that does happen sometimes, right? So these are some PRs that came like that, where, for example, we didn't have any idea to do regular expressions, and suddenly someone came and said, here's an awesome regular expression library that's like twice as fast as all these other ones. And we were excited. Another time, someone came and did a huge refactoring and replaced the whole compiler, basically, while we were looking. And those are really cool, right, when that happens. But sometimes it works out a little differently, and someone like opens the PR, and you're kind of like, that's not the direction we wanted to go. That's a nice idea, but and sometimes it works out sort of like this, right? Like nothing. Like you said, hey, I would like some contribution. Maybe you opened an issue and described the thing you'd like done, but nobody ever comes, even if people are paying attention to your project, right? So Rust has always had the benefit that people are interested in it. So that helps, but it's still the case that I've opened bugs that sit for years. They're like not a lot of work, and they don't get fixed, right? And I think the reason is that serendipity doesn't really work for everybody. Some people have an itch they want to scratch, a thing they want to add, and that can be great. That can also be the case where like this weird dog comes in, because that may not be a thing you wanted added. But a lot of people just want to get involved in the project, and they don't necessarily feel qualified to go pick up and develop a whole idea of their own. And so what we would like to think of it more as not open source by serendipity, but by design, right? Creating inroads for people to get involved and highlighting the opportunities and things you would like them to be doing so that they're actually doing those things. And there's a few steps to it. I think the first one is maybe step 0 is sort of realizing what a wealth of people there are who would like to be involved often in your project, and often with skills that you wouldn't necessarily think. So we initially thought, for example, that we wouldn't be able to run our sysops in an open source way because that would require giving keys and so on. But it turns out like, we are now doing that, and we've found ways around a lot of those problems. And that's been great, because now we have a lot more people who can help debug the CI failures and so on, right? But when you want to get them in, essentially recognizing what you can mentor out, and making a space is very important. So what I mean by make a space is like, don't just say, this is what I would like done, but help people with the first few steps. One thing we often do is something like a quest issue, where you will open up an issue and put a whole bunch of things. This is kind of great if you have like a road task that needs to be repeated a whole lot of times, like port all these tests to the new infrastructure or something. Put up a list, you put up instructions, do 1 or 2 of them and write up how you did it. And then people will come and they will do it because now they have a concrete model to follow. Right? And if they have 30 minutes, they'll start checking them off. Another technique that I think is really effective is building a skeleton. And by that I mean do the work, build the sort of the path you'd like to see, but leave lots of gaps. Don't try to make it complete. And then you can say, hey, now you can start to see what I'm thinking about. People can come fill it in and then evolve it. Right? So making a space is good. And when people do arrive, it's important to recognize them. And I mean both sort of tell them how awesome they are and how great, how much you appreciate it. But I also mean, think about, like, if they've been doing a lot of work, they probably have insights, right? And they should be brought up and involved in the leadership of the project. And that brings to the last point, which is if you want to keep the product kind of coherent, you have to articulate the vision that you have out so that people know what it is. Because a lot of times we have a lot of great ideas that we keep inside, and and this is how we imagine it doing, but we never set it anywhere, right? And people will start to make their own plans. And if you don't put your voice into the mix, then that can be a problem. And I think a good way to do this is just make as much of your planning public as possible. So one thing that Rust has started doing that's been really helpful for us is writing up yearly roadmaps. And we have a process that leads up to it where we sort of plan out, these are the things we're going to do this year, and we get feedback on what the priorities ought to be. And one of the great things about doing this is it lets us say no also. Right? So it gives us an idea of what to do, but then if somebody comes in and says, I would like to add whatever, higher kind of types to the language, not that that's ever happened, which maybe we will, I shouldn't say that. But we can say, sorry, that's not like, that may be good someday, but it's not part of our current roadmap. Right? It doesn't advance any of these goals. But there's a little secret that I should tell you, which is that the nature of the work will change. And success, if you are really successful at building an open source project, it's going to feel different than it did when it was just you hacking on your GitHub repo, right? I don't know if you can read this in the back, but this says, have you ever felt like you were born to do something? And it says, yes, heating and air conditioning. And that's kind of like, for a lot of us, I don't know, I think doing a lot of this work ends up being mentoring, it ends up being or organizing meetings, writing things up. It's kind of more managerial in nature. And I think there are ways to also mentor that kind of work out, but that is something that will change. Right? You're not writing as much code. But the good news is lots more people are writing code, so a lot more is getting done. But there's another way that it's painful that's a little more insidious, which is that initially, like, it was all you, right? It was your project, and you had it, and now these other people are coming in, and they have their own ideas, and it kind of feels sometimes like you're not sure how you feel about that, right? And this has happened to us a few times, even though we think we're aware of this. And sometimes you will find that you are actually kind of squashing people without meaning to, or just not providing avenues for people to contribute. So we say this thing to ourselves, the core team must, but the core team can't, which was articulated by Florian Gilcher, I think, hopefully I pronounced his name right, who we call Skade most of the time by username. And it had to do with conferences, conference planning at the time. But basically the problem is like, you see some problem you think you need to fix, and it's so important that you think you better do it yourself, but you actually just don't have time to do it right now, so it just sits there, and nobody can work on it because you're not giving them a road because you don't want them to do it. They might mess it up. And that doesn't get done, right? And it would be much better if you could find a way to let those people work on it, and maybe you can find a way, a compromise that allays some of your fears, like they should run back their plans by you afterwards or something. And that's one way it can manifest. There are other ways. But I think there's a sort of a meta lesson here too, which was when Florian wrote us the email, which kind of resulted in us writing up this rule for ourselves, it was a kind of a flaming, angry email. And I think many of us got it, and we were like, oh, you know, I don't want to read that email. That's horrible. I hate when people yell at me. And that's true, and that will happen. But one of the things we've learned over time is that if people are really angry at you, you might be doing something wrong. Like, they're expressing themselves maybe not in the best way at that time, although Florian was actually pretty polite. But, you know, but that doesn't mean, and you can react to that, but it doesn't mean you should look and see what led them down this. Maybe they were very happy and you know, they're just looking for a way to help, and you kept saying no, or you kept finding, you know, not like giving them avenues where they could participate, right? So I sort of say, it's not you, it's me, but it's maybe a little bit you, because it's on all of us to like participate nicely, right? This is not a one-way street. The leaders have to think about that. They have a little extra burden, I think, but the community members also need to, you know, think about how they express themselves sometimes. So it goes both ways. But I think the main thing is to be aware of that and be ready to admit when you are wrong. So that brings me to making decisions. Being ready to admit when you're wrong is a good theme. So this is like a key to any project is, how do you make a big decision, and how do you have that decision have legitimacy? How do people view it as a decision that was correctly made, even if they don't agree with it necessarily? And the way we've sort of evolved, the way we work right now, is we have a whole bunch of teams covering different areas of the project. There's language design, compiler, tools, community. This is not complete. There are many. And there's also a core team that covers like in cross-cutting concerns. And these teams, their main job, besides sort of working on stuff, is making formal decisions. So we have this RFC process. People can open a request for comment, an RFC. It lays out a proposal. It could be a change to the language. It could be kind of any major decision. And it talks about why this change should be done and other details. And there's usually a lot of conversation, right? And then eventually a decision is made. And one of the things we've learned over time, though, is that just having an RFC process by itself is really great, because it lets you, even if you're the only one using it, because you're at least writing down what you think. And it gives people a place to make proposals, and you can redirect them, and it's just a great thing to have. But it's possible to have an RFC process and not really use it correctly. There's a story that we sometimes tell from where we did that. And it basically comes down to, even as a team member, you should be participating in this RFC process. One way to look at it is the difference in experience between a team member and a non-team member should not be very big. Everybody should sort of be working on an even playing field. And so one time, right around the run-up to 1.0, there had been these huge community threads debating what to call our integer type. Okay? So it used to be called int, now it's called isize for the size. It's called iSize. And there was a lot of discussion back and forth on the various possibilities and the pros and cons. And what we thought was, this is like a distraction, this is a bike shed, we're just going to settle this. So the way we're going to do it is we're going to write a really well-reasoned message that's going to convince everybody. The final say, you know. And so I wrote this article that was like, we've been reading these threads and we believe we've come to a final decision. Like if you find yourself writing these words, that might be a red flag. So what happened was, of course, people were like, what the heck? You know, we've been talking about this for 6 months and you all think you can just waltz in here and like tell us the answer? Like we haven't thought of that before? And it was true. So this was Gabor, a community member, and they wrote that there was almost zero participation from the core team, which was true until that one comment, right? And basically, we realized that this was a case of us realizing, no, you know what, it's actually us. We're getting flamed and we deserve it because, so we went back and we started participating more, right? And our principle that we work on now is what we call is no new rationale. And basically it's, you shouldn't announce a decision, a final decision, unless the reasoning behind that decision has already been made public sometime before and people have had a chance to respond to it and tell you why actually you didn't think of some corner cases and so on, right? And so essentially, if you have a new idea, you should put it out and then make a decision on it later. Don't put them together. And so what we try to operate now is, our major goal is to achieve consensus, right? But not consensus about the final design, that's usually impossible, but rather consensus about the solution space. What are the different options we have and what are their pros and cons, and is there a third way that captures them, right? And if we can achieve consensus on the thread about this, then we know we're doing a pretty good space. And so you sort of watch for when the same comments are being made over and over and over again, that's like, no new stuff is coming up, you've reached a fixed point, okay? And at that point, that's where the team comes in, right? Is that their role is sort of to look at these, now that we have a map of the space, figure out, okay, which pros are more important than which cons, and what's the ultimate route we should go. And I think this usually works pretty well, especially if you can write up a final comment that sort of makes it clear that you understand all the concerns people have, and you just weigh them this way, right? And that's great. It's not trivial. I'll tell one story of a recent design, that sort of has the best of both, what we love to see in the RFC process and what we don't love. And I think this is very much a place where we're still iterating and trying to figure out the best way. But we were trying to redesign some details of our module system and to make it easier for people to learn. And we wrote up an RFC after doing a lot of design work. It was popular, but not that popular, and there were a lot of people who hated it. We wrote up a second RFC that was refined, took away some of the ideas, kept the things people liked. Okay, that didn't quite make it either. And we wrote a third RFC, and this one sort of hit the spot. Actually, it's what we're winding up shipping now, so we're doing a big release. I should have probably mentioned this. Rush 2018. It's coming out just in the nick of time to be released in 2018, in December. But you know, and I think in the end, everybody was happy with this design. Like, both the people who hated the original design and the proponents of the original design were happy. We reached a better design than we started with. So that was the good part. But there was a lot of like hurt feelings, right? I think from some people who were commenting, it felt like the big bad language team is like coming and taking their language and messing it all up, making it easier to use. No, sorry, I shouldn't express my no, just taking away, changing the features, right? And to the team, it also felt like big bad commenters were like not letting us do things. We have these great ideas, and they're just angry about it. And so that's sort of not good, right? We're sort of hoping for like something a little more like this, where you'll notice they're actually taking it from one another, but they're like calm about it. And after a while, I think it's right about here, they start to, you know, actually hand it to one another. That's our goal. And we've thought a lot about it. It's not clear what the answer is, if there even is an answer to some of these problems. But Aaron wrote Aaron Turan, this great blog post series where he sort of looked carefully at all the factors in this debate and identified these three things that come together in the worst threads where the fighting gets intense. Most threads are great, but in those few where it's really bad, what are the things that come together? And there's this sort of three-part piece. One is like momentum, where people have the feeling like, because the change was even proposed, it's sure to happen. Or alternatively, you make a proposal and the first comment is bad, and suddenly it's like a stream of bad feelings. And then this sense of urgency, like it's going to mess up the language. People take languages very seriously, which is good, but they feel passionately about it. So there's like this huge train of a change, and you have to stop it, and it's all up to you. And that's why people get so intense about it. And then there's this sense of fatigue, which happens after 3 or 4 RFCs, where everyone's just getting a little worn out also, right? And so we're wondering if we can adjust the process to try to increase cooperation. I have some ideas. I won't go into them in too much detail, but I'm inspired by TC39. So TC39 does the JavaScript language design, and they have a really cool process where they involve these explicit stages of discussion. And we actually have these too, but they're not as clear in our process. The idea would be to try to build up a community early on of people who are working on a design, who have different opinions, but they have hopefully some shared goals. They all want to see something happen, right? And iterate more. So that we have no, like right now the RFC point can feel very important. I'd like to basically have more decisions of lesser urgency and lesser weight, so that they're not as pricey. But we'll see, that's, like I said, that's something we're working on now. So if I had to pull it all together, I would say this about open source. It's not easy, right? But it is awesome. And if it really is working, the scale is like unprecedented. It's like the whole internet is there to help you, right? So the number of people who contribute to Rust, who have contributed is, I don't know, actually thousands. But the number of active contributors is very large, and the number of insights that people bring is tremendous. But to do it well, it's not going to happen by accident. So you need to do things like making these inroads, thinking carefully about we'll just walk through, what would I feel like if I came to this project for the first time? How would I know what to do, how to get involved? And one of the places that we're finding hard is we're pretty good now about that first interaction, and we've been forming these working groups, which helps for the second and third interactions. So a working group is like a cluster of people, like for example, implementing a new language feature. Right? And that means that now I fixed one bug, and I have a good idea of what bug to fix next, and it's in the same area, so I'm using my skills that I gained. But to go from there to like generally contributing to the compiler as a whole, for example, is a hard transition, and that's something we're still working on. But we want to articulate, make it clear what you think the vision should be, and be prepared for pushback, right? And that's okay, like you can work through the vision together. And that's exactly where this no rationale thing comes in, is when you're making these decisions, just participate in the discussion to the extent you can as an equal, and not try to like leverage your weight. And finally, I would say this idea of watching out for where you might be blocking people from getting involved. So, all right. That brings me to the end. If you're interested in learning more about Rust, there is now a variety of books. I think this is probably incomplete because these slides are a little old. But in particular, there's a really great O'Reilly book and a good book from No Starch that I've read. The other ones I haven't read, I'm sure they're also good. I have some screencasts, and there's a ton of Rust learning resources. And I'm standing right here in front of you, and I'll be here for the rest of the conference, so you could come ask me too. So thank you all very much. I guess we have a little time for questions, if people want. You in the front.
Yeah, so you showed a graph where you basically ramped up the number of contributors, right, and people in teams. That's great, but this seems like all the kinds of things that you need to know for a large open source project. Because that's not where you start, right? So when, do you have any idea when to start applying this? When do you start from a one-man project, and where do you start to add these processes, which are, well, from some perspective, an overhead. I mean, they're very necessary if you have a lot of contributors, but
right,
you know what I mean?
So the question is, when do you start bringing in these heavier weight processes, and sort of what should you do in the very beginning, especially? And I think the answer is not too early. They are overhead, but maybe a little earlier than you think, and then you can sort of, it's not fixed in stone. So what I would say is, the stuff about growing a team, mentoring, making space, that you probably can't do too early. The only time a way it would be too early is if like literally nobody knows that your GitHub project is there, so you could open a bunch of issues and have the best instructions ever, it won't help. Although you might be surprised. But yeah, but like if there was anybody who might be coming to help at all, then I promise you it will work better if they have some inroads. And you can maybe you're 100% available, so all you really need to do is say, ping me over on whatever, my Discord or Zulip or IRC or whatever you are, ping me over here and we'll chat about how to do it. But even then, you'll probably be happier if they have something to work from. So that sort of stuff you can do early. I think something like teams that can wait, or something like RFCs and teams, I'm kind of wrestling with this actually already on some of my own projects that are not Rust. I think that RFCs are probably good. So for example, that Rayon project, which is used by a lot of people, but doesn't get that much design because it basically works now. I would like to add RFCs there, because I think when we're making a change, it would help us to write out our reasoning. Right now we make these sort of ad hoc decisions on PRs, and it doesn't feel like we're really being careful enough. Even if nobody but us comments on the RFCs, I would like to see them, so we can write down our design, our thoughts. So I think you can do that early, and you don't have to adopt a heavyweight process for it. If there's not a lot of people talking, you won't need too much. It can just be you and a few others who are the main contributors. That's the core team. You make the decision. You don't have to fret too much because no one's going to get too upset. But as your project grows, then you're in place to grow the teams. I mean, we started out with very few teams. Now we have tons. And we didn't have working groups. Now we do. So I think it's not something you have to. You can adapt it. Since when it feels right, you take it.
I have a question about ownership and higher order logic. So can you have a sense of sub-ownership? Let's say I don't want to take ownership of the whole list, but I want to take ownership of one individual element at a time and apply a function to it.
Okay, so the question is, can I take ownership of one element at a time of a list and apply a function, and am I going to be then replacing these elements? Is that the idea? Yeah, so that's actually an interesting point, or interesting place in Rust design. You can take ownership of something by taking it out, and you can put it back, but you have to leave something in its place, sort of, depending how, like a vector you can pop off the end, and that just makes the vector smaller. But if you want to take something from the middle and not disturb the rest, then you have to replace it. What you can't do, at least currently, is take ownership of something in the middle, execute some code, and then put it back, because there's always the possibility, at least from our point of view, that that code might panic or fail in some way, in which case it would unwind the stack, destructors would execute, and they would observe this sort of hole. So usually what happens is you use the mutable references, which you can do that pattern with. And then there are some crates on some libraries that, given a mutable reference, they will let you take the ownership of the thing that's out and return it back. But if you should panic, so if you should be able to observe that there is a hole, they will kill the whole process and have a heavy weight. And a lot of people don't really care about panics because we don't encourage recovering. So there are some techniques, but they're somewhat limited by the fact that if you want to recover from exceptions in this way without killing your whole process, then there's this tricky part. So, but usually what people do is swap in a placeholder. So you might put some value that's like poisoned. That sort of moves the checking to runtime effectively, because if you observe the poison value, then you'll panic. So it's not the perfect fix.
About the process, you said that it doesn't work from the beginning. You have to start without this overhead. So can you see it in some way as if you have a new reference to the design of Rust, and then you change it, other type of
Can I view it as if you have a mutable reference to the design of Rust that you adapt over time? I suppose I could.
then it was time to
Right. Yes, I think you can see it this way. I mean, you certainly have the right to change it, sort of, but you have to. The trick is knowing when to change it. But I would add one thing to that comment I was thinking about a little more. As an example, there's a new project I'm working on, and in that project, I'm not doing full RFCs, but I have issues where I'm writing out and encouraging people to give me feedback. And there's only a couple people looking at it, right? But there it's like very lightweight. It's not even really a procedure, but I'm still trying to have the sense of an RFC. And if I'm just writing it, of course, writing out what I want to do helps me. Anybody else? All right. Well, thank you all again, and I'll see you later.